Yeah, thanks very much to the organizers for asking me to speak. I'm Phil. I work on the PureScript compiler in my spare time, and I work on Haskell for a living. So, if any of those two things are interesting to you, come talk to me about them. If you want to see the slides for this talk, you can go to GitHub. It has the code that I'm going to show, and it has all the markdown for the slides and stuff. So that's my username, CodeMesh 2016. And I have the same username on Twitter and GitHub, and you can meet me on PureScript IRC most of the time as well. OK, so let's talk a little bit about the problem we want to solve. And the problem I want to solve is a specific version of trying to port some interesting techniques from Haskell to PureScript and getting over the problems that you encounter along the way. OK, so consider this Haskell function. Okay? It's a common function. It's in the base library. It's called replicate_m. Is this working? There we go. OK, so it's called replicate_m, and it works for any monad. So I'm going to assume a little bit of Haskell knowledge in this talk, but hopefully that's OK. So it works for any monad m, and it takes two function arguments. Okay, it takes an integer, which is the number of times I want to repeat an action. So that action might be, well, it can be in any monad. Okay, so it could be I just want to log something to the console, or it could be generate a random number, or it could be something in like the maybe monad, for example, right? But I want to replicate that n times, discarding the results. So that'll give me an m returning unit. Okay, so a result with essentially where we're discarding the, we're only considering the effects, and we're discarding the result type. Okay, so it's just defined recursively. We say if the number of times we want to replicate the action is 0, then we don't care what the action is. Just return nothing essentially. But if it's anything other than 0, so not negative though, then just perform the action once. So x is the action here. Perform the action once, and then, so this is the bind operator from Haskell, replicate n minus 1 times. Okay, so this is totally fine in Haskell. So this is totally fine in Haskell, and we can test it using GHC or GHCI. Okay, so we can say replicate 10 million, 100 million, something like that, number of times this just action. So maybe is a monad, and just is an action that is essentially the action that does nothing in the maybe monad. So we can replicate that a bunch of times and print the result, and we can run that, compile that with optimizations, and run it on the command line with this runtime option -s, and see what the runtime does. Right? So it says, OK, well, this is the answer, which is what we expected. It only allocated this small amount of memory on the heap. Right? This is actually, I'm pretty sure, sort of the minimum required by the runtime to sort of set various things up. But it didn't allocate anything else, even though we were doing whatever 100 million actions. Right? This basically just got compiled into a very tight loop. If you actually dump the core from GHC, you can see that it basically just compiles it right into a while loop. Okay, so this is really good. And you can see various stats, right? So the mutator thread took up 98% of the time that was spent by the runtime. And there was no garbage collection, because it didn't need to garbage collect because it was just a loop. Okay? Nothing was allocated. Okay, so if you're like me and you work in Haskell, but for one reason or another you want to work in a strict language on some target like JavaScript, like you would in PureScript, then you might ask, well, can I port this, function to PureScript, and is it safe to do so? Right? So I'm not really going to talk all that much about PureScript in this talk. The code will be in PureScript, but if you're not familiar with PureScript, then it's a strict language. It's based on Haskell. The compiler is written in Haskell. A lot of the techniques that we use are inspired by Haskell techniques. And for the purposes of this talk, crucially, it has type classes, and it has higher kinded polymorphism. Right? So those are the only two things that you'll need to actually use the techniques from this talk. So you could use PureScript and compile to JavaScript, or you could compile to one of the other backends. So we have a C++ backend. We have an Erlang backend and a couple of other sort of experimental ones. Or you could use Scala or Idris, all strict languages with these features. Right? I'm not sure if there's any others, but if you have these features, then you can use these techniques. Right? If you're interested in PureScript, then there's a page on purescript.org that has sort of a list of resources and all the stuff you need to learn about it. Right? OK, so PureScript looks a lot like Haskell. Right? This is You have to look quite hard to figure out the differences here, but this is basically the function that we just had naively ported to PureScript. Okay, so there's not much in the way of differences. You have to explicitly quantify type variables here, and then this operator changes slightly because it comes from applicative. It doesn't come from monad anymore. I think and unit has a name. It's not a built-in symbol. But apart from that, it's pretty much exactly the same. But it doesn't behave the same, right? So if you run this with 100 million or something, then you get this problem. Immediately, pretty much you just get a stack overflow, which is sort of what we'd expect, right? The language is strict. If we think about the evaluation, you should always sort of think when you're writing pure script, what would the corresponding JavaScript look like? So essentially, this just corresponds to a function application. This operator becomes a function application to the recursive call of replicate m. Okay, so we're just building up this big sort of thunk, essentially, by recursion. So we run into a Stack Overflow. Okay, so we can see that. I'll just give a little demo. Is it this way? Okay, there we go. Is the font size okay? The back? Yep, cool. All right, so this is try pure script. If you want to, you can't really read that, but if you want to test out little code samples, this can be really useful. It comes with all the core libraries built in. So you can just sort of change stuff here and it recompile on the server and send back some JavaScript and run it. Okay, so we can, I've got some code samples here, right? So here's replicate. That's the good version, so let's hide that. So here's replicate, and it's pretty much exactly what I just wrote out, except for I used do notation at the bottom there. Right, so we can do something like, say, replicate m 10 times, replicate with an e. Should work. Okay, and we get 10 of the same string. Okay, so that's fine. So it just went to a sort of stack depth of 10, so we wouldn't expect that to Stack Overflow. But if we do something like this, okay, then it'll think for a little while because the way try pure script works, it basically just treats the console like a big string in memory. So it's okay for a while, right? And then we get to the bottom, and we get that error that we expected. Right? But there's a way to fix this, so I need to make sure I don't crash my browser here. I'm pretty sure this will fail as well, so you know I'm not cheating. Okay, good. If we take this safe version at the bottom, which I'm going to walk through in a second, now it should start working. Okay, yeah, so it'll think for a little bit, because it's building this sort of big string representing the console in memory. But eventually, when it's done, actually, I hope I tested this with 100,000. I have a feeling I might have done it with 10,000. But OK, cool. Right, so it gets to the end. It takes a little while and thinks because it's sort of building this massive string. But now this new version is safe. Right, so let's go over why that's safe. OK, so you might think if you've sort of done functional programming in strict languages before, well, it's obvious, right? You didn't make your function tail-recursive. So to a certain extent, that's true. Right, so if you're not familiar with the term, tail recursion means that your function is recursive, but it's only recursive in places. It's only basically it only makes the recursive call as the very last thing it does in the function body. Okay, so a tail recursive function can either at the end of a tail recursive function, you can do one of two things. Right? You can return a value, or you can loop. And if you loop, then you can modify some function arguments, and this is a little bit like changing state in a while loop or something. So the compiler can recognize these cases, and it just turns a function like that into a while loop, right? If you look at the generated code, it actually just becomes a while loop. Okay, so for example, we could take replicate m and modify it so that it uses a loop, right? So here's my loop, and I start with pure unit, and I pass along as an accumulator the number of sort of replications of the action that I still need to do. Okay. So here's my accumulator, and if it's 0, I just return the accumulator. If it's non-zero, then I loop, but I change my function argument here so that I tack on another instance of the action. Okay, and I change my other argument to be n-1, and this behaves the same. Okay, so this works in some cases. So if you have a monad like maybe, where evaluating a monadic bind is essentially doesn't have any additional cost, you're not sort of deferring any cost, then this is fine, right? So you can say this and you get an answer back very quickly. But it fails for other monads. We have this monad called f, which is basically like our I/O monad. And it's sort of not immediately obvious why it would fail for f, but we do get a Stack Overflow. And the reason is that while we can sort of build up this sort of big effectful action in our monad with a big while loop, the actual evaluation the while loop, sorry, the actual evaluation of the action when we're done is still basically a big stack of actions, right? It's still essentially a big nested function call. So in this case, we actually do still get a stack overflow. So I want to demonstrate a technique that allows us to do things like this for a certain class of monads without any of these issues, right? Okay, so I said earlier that a tail-recursive function has two options when it's about to finish. It can either return a value, or it can change some function arguments and loop. Okay, so we can just reify those constraints, right? Those two options, we can just turn them into a data structure. I can say that a step in a tail-recursive action, so this is basically either, right? But we used to use either, and we changed the names of the constructors because we always sort of forgot which one was which. But you're either done, and you have a return type of B, or you can loop, and you have an argument which you might change of type A. Okay, so those are the only two options that you have in a tail-recursive function. Okay, and then once we have that data type, we can write a general-purpose tail-recursive function that basically generalizes every tail-recursive function of one argument. Okay, and it's called tail-rec. We say, okay, so for all types A and B, A is going to be your input type of your function. B is going to be the return type. I can build you a function from A to B that's tail-recursive if you can give me a function that for every state A gives me one of these two options that says you can either loop or you can say, I'm finished. Okay? And once you have the version for one argument, it's easy to sort of build versions for multiple arguments. So you can say things like if you have two inputs A and B, and you want a return type of C, and you can give me a function from an A and a B to a step that returns another A and a B, or finishes with a C, then I can give you a function of two arguments that's tail-recursive. Right? So we have various versions of these things. And then once you have that, it's a little bit noisier, but this is a safe version of sorry, not quite. Okay, we can write replicate M like this. We can say it's a tail-recursive function of two arguments defined in terms of this function loop that starts with pure unit, which is this computation that does nothing, and the number of times I want to replicate. And it loops a bunch of times, decrementing the count and adding on to the number of modifying the action to add on one more occurrence. And then finally, it's done. When we get to 0, it just returns the accumulator. Right? So this is just another way of expressing the tail recursion that builds up that big action, but it doesn't actually fix the problem that the action itself is going to run into a stack overflow. Okay. Okay. So now the sort of trick is that we want to generalize this tail-rec function to what we call monadic tail recursion. Okay. So we take this tail-rec function that we had, and we build it into a type class that's a subclass of the monad type class. Right? Actually, in Scala Z, I think they actually moved this into the monad class. I think the cats library implementation certainly does it that way. But essentially, we have this function called tail-rec-m for monadic tail-rec. Okay, and it's exactly the same as tail-rec, except for that we're building a monadic function, right, like a Kleisli arrow. Okay? So it takes an input A, and it returns a B in some monad. That's one of these monad recs. Okay? In order to build it, you have to give me a function that for every step takes a state and gives me back one of these step things that tells me whether I want to loop or finish. Okay? But it can have monadic actions at every step. Right? So I have some state, and I can step once, perform some monadic actions. Where's my thing gone? There. Perform some monadic actions and tell you whether I want to carry on or finish. This function will sort of put all those things into one big monadic action, and hopefully safely. Okay? So we can ask what the laws for a class like this should be, right? Type classes usually come with laws. Well, a sensible law for this class is that it should be equivalent, well, sort of observationally equivalent to this sort of default implementation of tail-rec-m that we could just provide given the monad instance, right? So if you have a monad instance that isn't going to blow the stack, let's say, then maybe you do this like this. You take your function, you just run one step, and then case on the result. And if you were done, you'd finish with pure. And if you weren't done, then you'd make a recursive call. Okay? But the idea with this class is that hopefully we can come up with a more efficient implementation, right? And for a large class of monads and monad transformers, we can. Okay? So ideally, in fact, we do it without using any recursion in the tail-rec-m implementation whatsoever, right? And then we can say that the laws allow us to sort of reason about this by saying, well, it uses tail-rec-m, so I know that this won't grow the stack more than f itself will grow the stack. Okay, so it's a nice little way to sort of reason about the stack usage of our functions. Okay. So I don't expect you to understand this pure script code, but there's just sort of one interesting thing about this. So this is the implementation for except t, which is an error monad transformer from the pure script core libraries. And this instance says that if the monad that you're transforming, M, is a monad rec, then the transformed monad that also tracks errors is also a monad rec. Okay? And it's just defined in terms of tail-rec M for the underlying monad. Right? So if we're sort of trying to bootstrap this concept, then we hope that the monad inside the transformer is not using recursion to implement tail-rec M. So this one isn't either, right? So if you look at this, we use tail-rec M, but we don't actually do any recursion in here. There's no call to tail-rec M itself. We're just sort of plumbing through the lefts and rights from the either that's wrapped up inside the except t. Okay? So this basically amounts to sort of doing tail recursion with the option of bailing out at any point with an error. Okay? And we can do this for a bunch of other monad transformers. Right? So we have this sort of rich class of these monads for which we can implement tail recursive functions without growing the stack. And we can build a big monad transformer stack. And if we know that we have monad rec instances for all the pieces of our stack, then we know that overall we're not going to grow the stack more than our sort of seed function that performs one little step of our tail recursion. Okay? So we can do monadic tail recursion for the identity, because the identity, you know, it just wraps up the type argument. So essentially, tail-rec M just becomes tail-rec. We can do monadic recursion for the state monad transformer. So this basically amounts to sort of adding an additional accumulator parameter, if you like. We can even do it for writer. So this is a little bit like, if you're familiar with the idea of tail call modulo cons, it's sort of a little bit like a generalization of that. It's like we're allowed to do tail recursion, but we're also allowed to sort of append something onto a monoidal accumulator value in the return value before we do the loop. Okay. Reader, it's not very interesting, but it's handy to have this instance. So I already said F is our monad from PureScript that's a little bit like Haskell's I/O, and you can give an instance for this. So this sort of makes sense because you know, you expect that you should be able to sort of interleave native actions from the JavaScript runtime inside your tail recursive function. And this last one's kind of interesting. So this is a library in the PureScript ecosystem that essentially implements like promises or futures or something like that. So it's like an asynchronous effects monad. And this is really handy, so I'll get onto an application of this later. But yeah, essentially you can think of this as like a monad for solving sort of callback hell type problems, right? Like a promise or a future monad. Okay. Okay, so now that we have this class and we have this idea of what a tail recursive monad is, then we can change replicate M, and we can write it in terms of monad rec. Okay. So now it's just a simple application of tail rec M, where we just pull all the logic from before into this loop function here, right? So loop says if you're on 0 as your accumulator, then I'm done. Or if you're on n, then perform x once and then loop and change my state to n minus 1. Okay, so this is pretty simple. The trade-off we've made is that instead of doing this for an arbitrary monad, now we have to do it for a monad rec, so only one of those things in the class from before. But that class is pretty big, right? So it's not too much of a trade-off. But the big win is now that for all of those monads, now we can do replicate M and not worry about the stack. Okay? So this is stack safe, as I said here, for any law-abiding monad rec instance. Okay? And you can go through the same sort of steps with functions like mapm or traverse or foldm, and sort of build up this library of simple functions that you can implement as tail recursive. Okay, so that's nice. And now we have this sort of simple library of functions inspired by Haskell that we know aren't going to grow the stack, okay, even though they work over an arbitrary monad. Okay, so I already covered this, but it's nice to have this sort of dictionary of mappings from sort of monad transformers to sort of an intuition about what style of recursion we're doing, right? So, like I said, state t sort of corresponds to adding an additional accumulator, like an additional parameter, like an additional argument to our tail recursive function. Writer t is this sort of variant on tail call modulo cons, and except t is just like a tail call, but where you can essentially throw an exception in the middle of the tail recursion. Okay. All right, so that's that's the type class and the theory of the type class out of the way, right? So let's see some places where we can apply this. Okay, so the first application is to free monads. Okay, so if you're familiar with Scala and Scala Z at all, then you might be familiar with the solution that they have there for making free monad computations safe and stack safe. Okay, so this is a slightly different take on that. And as I understand it, I think this sort of generalizes to more monads, but it might be possible to sort of get around that by trampolining, so I'm not 100% sure. But this is the first application. Okay, so the free monad is defined in Haskell like this. Okay, it's defined in layers, and a layer can either be a pure value that says I'm finished. This is the return value I want to return, or it's impure, and the free monad's parameterized over some base functor. Okay, it's free. It's defined in terms of this functor, and then an impure computation is a functor full of more computations to do next. Okay, and you can. So I'm not going to go into too much detail on this. But if you're familiar with free monads, then hopefully this should make sense. And you can define an instance that says, if you have a functor for f, then you can make free f into a monad, okay, for any functor. And you have an action that says, if you have a functor, you can also lift a value inside that functor into a value in the monad. And then you can use do notation to plumb these things together, right? And it's just defined like this. So you can say, I have one impure layer that does some effects, and then the next layer down is pure, essentially just returning the value given by the functor. Okay, and as I said, it represents sequences of instructions, and the instructions are defined by the base functor. So what sort of functors are we sort of thinking of here? So something like this database f, right, which we might use to track things like inserting and selecting values out of a database. Okay. So this is a functor, and it has a type argument, right? And the type argument represents what to do next after this first step in the computation. Okay. So if we do an insert, then we need a key and a value to insert into the database, and then we need a thing to do next. And if we're doing a select, then we need a key to select, and I only figure out what to do next once the database returns and gives me the maybe value that corresponds to that key. Okay, so I have a function that says, here's the value, now tell me what to do next. Okay. So we can give a functor instance for that, that's fine. And then just derive the monad instance with the instance we had before, right? Using free. And we can use lift free to insert, and we can use lift free to select by lifting these two actions from the functor. So that's fine. And then this is how this is the sort of generic function for running a computation in a free monad, right? So the implementation isn't particularly important, or the type actually, but just notice that this is monadic tail recursive, right? Run free is the last thing we do before we loop, okay? So we might hope that we could actually write this in terms of monad rec and not worry about the stack, okay? Okay, so just a little bit of motivation on free monads briefly. So one nice thing is that you can use them for testing. You can give multiple interpretations. You might have one interpretation that goes to the database and actually runs some SQL. Or you might want to use it for testing, right? And then I could interpret my free monad using run free inside some state monad that basically just tracks a map from keys to values in a state monad. And I've got an example here of a function where we can take one of these database computations in my free monad and turn it into the state monad just by using run free. Okay, so we just have to say what we do on each of the actions. When we want to insert something, then we do an insert on our map, modify the state in the state monad, and then do the next thing. And if we want to select something, then we do a get on the state, and then we do the next thing. Okay, so see how we're passing the value that we got back from get into the continuation here, and then that gives us what to do next. Okay, so they're really handy for testing. But as I just explained, the problem is that run free uses monadic recursion, right? So in most cases, unless your monad that you're interpreting in is stack safe for some other reason, you're going to have problems when using run free with deep computations or infinite computations. Okay, so there's this risk of blowing the stack. But instead, we can just, again, trade off the monad constraint for a monad rec constraint. And now we can interpret free monads in any monad that has a law-abiding monad rec constraint, which, as we said, is quite a large class of monads. Okay? And then, again, we know that if we have a law-abiding monad rec instance, then run free is always going to use a constant amount of stack. And I don't know if you've used trampolining sorts of solutions before, but personally I find them sort of quite tricky to figure out exactly when the trampoline is going to sort of make things safe or when it's not, because you have to sort of worry about where the monadic binds exactly are happening. But it's relatively easy to sort of look at the implementation of run free in these terms and just think about it in terms of Tail-Rec-M and figure out that it's always going to be safe for any Tail-Rec-M that's law-abiding. Okay, so we can go one step further, right? So this is something that, as I understand it, you previously couldn't do with the trampoline-based solutions, is go from the free monad to the free monad transformer. Okay, so what's a free monad transformer? Well, it's just like the free monad. So everything's sort of layer-based. Okay, so we have a constructor. It wraps up either a pure layer, which returns a value, or a functor full of next steps, essentially. Except for now, we have some base monad that we want to transform. And every layer, we can have some monadic effects from this base monad. Okay? So this is quite nice because it allows you to sort of separate the effects that you're interested in into two classes. The ones that I want to perform now, so that's the ones in M, and the ones that I want to interpret later and have multiple interpretations for, and those are the ones that I'm going to build the free monad part out of from F. Okay? Okay. And I won't go into the details. The applications are sort of more interesting. But essentially, the technique's exactly the same. Okay, so we just say, well, instead of working over an arbitrary monad, I'm going to work over a monad rec. And the implementation is monadic tail-recursive. Okay, so we can just use Tail-Rec-M, and it all works out. So like I say, I won't go into the details of this bit. It's a bit more involved, but the paper, which is linked from the repo, sort of goes into all the details on this. Okay, so because this works for any F that we're building a free monad transformer out of, well, so we can pick any F, right? And in particular, we can pick the identity functor. Okay? So we can build this type synonym safe T. That's the free monad transformer for the identity functor over some base monad. Okay? And if you sort of just expand stuff out, this corresponds to safety being, safety of M essentially being either, so there's some monadic effects from M, and inside you have either an A or another safe T. So if you went to Edwin's talk, Edwin's Idris talk, he mentioned a type called inf.io, and it's sort of very similar to this type. It's basically just a big tower of monadic actions expressed sort of one step at a time. Okay? The only difference is, in this case, we actually track the final return type because we're interested in potentially infinite actions, not just always infinite actions. But it's the same sort of idea. Okay. So the idea now is that since we can build this safe T monad transformer, and we know that free T is stack safe for any functor and for any monad, well, now if we want to perform some monadic computation that's recursive but not necessarily tail-recursive, well, maybe we can't do it in M, but safety M is certainly safe, okay? So we can just lift everything up because safety is a monad transformer. Every time we see an action in our recursive definition that uses M, we can just lift it up into safe T, okay? And we also have this function called lower that uses run free T, and which takes a safe T in some monad rec and lowers it down to an MA. We can retract this back down onto M, okay? So that means, as a worst-case scenario, if I have monad rec, maybe I can't write my function as tail-recursive, but I can always just lift it up to safe T. So we essentially get this notion of stack safety for free. Okay? So if you have a monad rec, not just the tail-recursive monadic functions, but actually all of the recursive monadic functions can be made safe. So if we're feeling lazy, we don't even have to use Tail-Rec-M. We can just write the sort of naive replicate M by lowering down a computation from safe T. But every time we see a computation that we're given in M, well, we have to lift it up into safe T. But this is stack safe by virtue of free T being stack safe. Okay. So this is a nice little trick if you you don't want to try and figure out exactly how to make something tail recursive, or maybe it can't be. Okay? And the nice thing is, safety has induced instances, things like monad state, monad error, they all get lifted up. So you can sort of always just shift over to this safety monad and get stack safety for free. Okay, last application is coroutines. Okay, so in the free monad talk earlier, somebody asked, all these abstractions are nice, but are there any applications where you don't need to understand the actual sort of free machinery in order to get the benefits? And coroutines are a nice example of that. Okay. So what's a coroutine? Okay. So a coroutine is like, the implementation is exactly the free monad transformer. Okay. It's something where we compute in steps, and every step we do some work. So those are going to be effects tracked by our base monad. And then we suspend. And what we do at the suspension depends on the funct that we're using to build our free monad transformer. Okay, so we might do things like emit a value. So we might, if we want to build something that's a little bit like an asynchronous generator, I forget what the thing's called in JavaScript. They're called generators, right? No, I forget. But if you want to build something like Python generators that can be asynchronous and have asynchronous effects, then you can do that using this producer type synonym. Okay, that's just a free monad transformer over some base monad, and we're fixing the functor to be this emit functor, and we track the type of the things that we want to emit. Okay, so emit is just, it only has one action, and we said that A was going to track what to do next. So every suspension, we emit an O, and then we have something to do next. Okay? So I'll give a demo of this really quickly, but this can be useful for talking about a wide variety of asynchronous generators in a nice way. So the dual to producers is the dual to a producer is a consumer, and if we want to do something like handling HTTP responses from a web server in a chunked way, then we might want to do it in terms of consumer, which is this idea of an asynchronous enumerator of data. Okay, and this is just exactly dual to producer, right? So again, it's defined in terms of the free monad transformer, and we use this. Oh, this is wrong. I'm sorry. This should say await, not consumer. But it's defined in terms of this await functor. Okay, and we track the type of things that we want to await, and at every step we wait for an input, and then we have a continuation that tells us, given that input, what is the next thing to do. Okay, so that's just a model of enumerating values asynchronously from a server or something like that. Okay, and then. Details on this slide aren't terribly important, but the idea is that we can take a producer and a consumer and just zip them together, right? The producer is going to asynchronously generate something, it's going to perform some actions and then emit an item. And a consumer is going to perform some actions and then wait for a value. Okay? So we can just zip those two things together, and every time the producer produces something, the consumer can consume it and have its effects, and then we go on to the next step and run these two coroutines in lockstep. Okay? And the details here aren't terribly important, but the implementation of this fuse function is monadic tail recursive, right? So we can actually give an implementation of this that works for deep free monad transformer computations, i.e. coroutines that run for a long or infinite time. Right? So this is a really handy way of coming up with a library for producers, consumers, various types of coroutines, and sort of stitching them together in nice ways. So we can do various types of fusion, and they're all safe. We can fuse two producers, and we can get a producer of tuples. Or we can fuse together two consumers, and we can get a consumer of tuples. Or we can fuse together a producer and a consumer, and get something that doesn't do anything when it suspends. It's essentially one of these inf-IO computations, right? That just has some effects at every step, and then we can just run that to completion. So why is this useful? Well, so it's useful because producers and consumers model a great variety of the sorts of effects that we want to track in languages like PureScript on the web. So we often deal with asynchronous things. So in particular, we'd like to be able to do asynchronous file I/O in JavaScript. And it can be tricky. You have to sort of deal with callbacks everywhere. But the coroutine machinery sort of hides all that away, and you don't have to worry about it. You basically just say, here's my producer. Maybe it comes from file I/O. And here's my consumer, and maybe it comes from a web service, and I want to take every chunk as it's generated and just push it into the web service. And there's all sorts of nice things you can build with this. So you can do, you can build coroutines for WebSockets. You can build coroutines for AJAX, both upstream and downstream. And I have a quick demo, but let's see how I'm doing on time. 5 minutes. All right. Yeah, should be OK. All right. OK, so I have a little snippet of code that I've already written here. So what's going on? So essentially, what I need to put here is a coroutine that I want to run. A coroutine that I want to run that's going to, for my example, I'm basically going to read a file in chunks and print it to the screen. And then we can show how we can do things like write a cat program that will read multiple files. But the important, what's going on with this? Yeah. All right. The key thing here is that we're reading in chunks. Oh, no. All right. Well, it's there 50% of the time, right? So it's OK. All right. So the key thing is we're reading in chunks and not using more stack than any of the pieces, any of the building blocks that we're using to build this. All right. So let's say we want to read a file. Well, I've got a helper function in my helpers module here. And this is one of my coroutines. It's a producer, OK? And I have to give it a file encoding that I want. No. I have to give it a file encoding and the file path that I want to read and the size of the chunk that I want to read in. This is no good, is it? All right. You know, I'm nearly at time anyway, so let me just go through the slides. Anyway, suffice it to say, you can just write something basically that says, build a read file coroutine that's going to be my producer, and fuse it with a printer coroutine, which is just going to print these things to the screen. That's a consumer. And the machinery just takes care of sort of all the plumbing, and it sort of it can run forever if you want it to. You can give it very large files without using too much stack. So you have this library of coroutines, and you can just glue them together in nice ways. OK, I'm going to skip the demo. All right, so I can wrap up very quickly. OK, so what's the conclusion? So monad rec is this nice type class that extends monad, and it can take a variety of tasks based on things we do in Haskell and make them possible in pure scripts. Right? It's a nice way to sort of port ideas from Haskell to pure scripts, or Scala, or other languages with those features that I mentioned. So crucially, it doesn't work for every monad. It only works for monad rec instances, right? So we always trade off the ability to do things for arbitrary monads for this sort of slightly smaller subset, which is still quite expressive. But on the other hand, we can always reason about our stack now. We always know it's safe. So if you want to use these ideas, it's available in the PureScript standard library. Scala-Z implemented them. The CATS library implemented them as well. And I think there's an implementation in the Fantasyland JavaScript repository as well. And if you want to see some of the details, and there's plenty of examples of sort of coroutines and things there as well, then there's a paper on my website, which is functorial.com, stack safety for free. So yeah, you can check that out. Or come and talk to me afterwards, and I can sort of show the demo as well, hopefully. So that's it. Thanks very much. And yeah, so find me on Twitter and etc. PAF31. So that's it. Do you have time for questions? Or?
Well, we have 1 minute until we need to get started for the keynote. We've got 2 questions. Do you want to fight? All right. I'm just going to get to the closest one because we really do have 1 minute. So you get 2 words.
This reminded me of Haskell's pipes library. Is there a shared lineage there?
Yeah, so if you look at the implementation of pipes, it's essentially, well, as I understand it, it's essentially just a coroutine. So then, obviously, there's a lot of operators for connecting pipes together, and the interesting stuff is all the nice, rich class of ways to connect these things together. But the implementation, I think, is just a coroutine with various types of things you can do at suspension, like read from the client, push to the server, write to the client, all these types of things. Yeah. But of course, in Haskell, you sort of don't need to worry about the stack safety bit, right? So, yeah. Or, well, there's different worries, I suppose, but yeah.
That'll have to
All the
do.
time?
Thank you, Phil.
All right.